So the first thing we got to imagine is somebody here is falling. Gravity is doing work down like this. If gravity was the only force acting on this object, or this person, this fat man in a red suit, he would continue to accelerate. However, the reason you reach terminal velocity is because the force of air resistance is pushing up on you as you fall. And at some point, these two forces are equal, and that's when terminal velocity happens. That's when you stop accelerating and you just fall at that maximum velocity. Because when the forces cancel out, it doesn't mean you stop moving, it just means you stop accelerating. Gravity's still doing work. But the net work is zero. How can that be? Because the work done by air resistance cancels the work done by gravity. So yeah, gravity's still doing work, air resistance is still doing work, but it's doing negative work, and they just cancel each other out. Okay. Devin Blinn, skating across a rink with an initial velocity of 9 meters per second. The mu sub k between his skates and the ice is 0.13. That's the coefficient of kinetic friction. And he's going to slow down because of that friction until the final velocity is until he stops. And the mass, not that I imagine we'll need it, but Devin is a healthy 30 kilograms. What is the work done by friction during the slide? Okay, so we can start with what kind of energy did he have? He has kinetic. He's going to lose that due to the work done by friction until he has nothing left over because he stops. So what is the work done by friction? Well, you can see that the work done by friction has to be the same as the amount of kinetic energy he has because he takes it all away. So let's figure out what his kinetic energy was. 1/2 mv squared, which is 1/2 times 30 times 9 squared. And my handy dandy calculator says that is 1215. 12152. Okay, so it's the work done by friction, so that is going to be a negative. Okay. How far does he slide? Well, remember that work is equal to FD. So if friction does 1215, negative 1215 equals, now the force of friction is going to be mu sub k times mg, and then times d. The d goes there, the force is here. So negative 1215 equals 0.13 times 30 times 9.8 times d. And now we just solve for d. It's going to be 31.79. So 31.79 meters. Okay. Again, if you're worried about the negative sign, remember that frictional forces are always negative forces, so you can manually put a negative on this if you want to. But the distance is going to be 31.79 meters. All right, jump into the next question. Pierce runs towards a 5-meter rope swing at 6.5 meters per second. Grabs on and swings upward as high as he can, assuming 18% of energy is lost through the friction. What angle will the rope make? Okay, another good time for a picture. So here is the theta that we're trying to find. Here we see that the kinetic energy is going to be transformed into the potential energy, but we are going to lose 18% of his energy. So if you lose 18% of your energy, it means you keep 82% of your energy. So 0.82, so 82% is 0.82 of his kinetic energy will be transformed into potential energy at the end. So now it's just time for our equations. We're going to have 0.82 times 1/2 mv squared is going to equal mgh. Notice that the m's will cancel out. So 0.82 times 1/2 v squared is going to equal, and let's say all this divided by g is going to equal h. And so let's just figure out this number off to the side right here first, and then we can figure out what to do from there. So 0.82 times 0.5 times 6.5 squared divided by 9.8 We get 1.77. So 1.77 meters is your h. Okay, but it's asking for the angle. So here we got to use some of the geometry of this rope swing. This is theta that we're looking for. This whole length of the rope is 5 meters. This height right here is 1.77 meters, which means that this part of the triangle from here to here is 5 minus 1.77. Right, because if the whole thing is 5, and this part right here is 1.77, that means that this part right here is 3.23 meters. So let me just erase that so it doesn't get too ugly. So now we're trying to figure out the angle. Well, good news is we have the adjacent side and we have the length. So cos theta is equal to 3.23 all over 5. So now we can just do the inverse cosine of 3.23 divided by 5. And let's try that again. Inverse cosine of 3.23 divided by 5. 49.76 degrees. So 49.76 degrees. Okay, here we're going to be making a video on this reindeer that we're going to drop off a cliff. After falling halfway down, its velocity is observed to be 35 meters per second, but it's still accelerating. What's the work done by air resistance during the fall so far? All right, so we have this object. I'm just going to do it as a circle. This object falling from a 200-meter cliff. Now, halfway down, its velocity is 35 meters per second. That's an equal sign. What's the work done by air resistance so far? So the fact that there's air resistance means that if there was no air resistance, we can imagine that it would be faster than 35 meters per second at that moment. But air resistance has been doing some work to slow it down. So let's take a look at our energy. We had potential energy. Now, as it falls, it's going to lose some of that due to the work done by air resistance. And whatever's left over at the halfway point right here is going to be a mix of its potential energy there, it's half, right? It's going to be the potential energy halfway down plus the kinetic energy halfway down, right? I guess we could just say top right here. So that's how we're going to imagine this problem right here. So we're trying to figure out that number, the work done by air resistance. So let's just solve it algebraically. That means we're going to bring that over here. That means we're going to bring these two things over there. So it's going to be PE at the top minus the PE halfway down plus the KE halfway down. And all that's going to equal the work done by air resistance. All right, so let's just do some numbers now. So it's going to be mgh. Actually, let's just do numbers. Sorry. So this will be m of 45, g of 9.8. The original h was 200 minus the mgh of halfway down, which is 100, plus a 1/2 45. Now it's only going 35 meters per second squared. That's going to be equal to the work done by air resistance. So now, yeah, it's a lot of numbers, but it's really just calculator work. So let me just crank this out real quickly. We got 45 times 9.8 times 100 plus 45 times 0.5 times 35 squared. It's probably going to be a big number. And that we're going to subtract that off of 45 times 9.8 times 200. So I get the work done by air resistance as 1,653.7.5 joules. And it's air resistance, so we're going to put a negative sign on that. That's what I get. It's totally possible that I may have put something into the calculator wrong, but this equation is definitely right. Hey, what's up?
I have to run grab
okay. So what's the average force of air resistance during the first 100 meters of the fall? So if work done by air resistance is equal to the FD, the force of air resistance times D, That means that negative 16537.5 has to equal the force, the average force, times 100. And we can see that the average force must have been negative 165 point, let's see, it could be 0.375 newtons. All right. What percentage of the reindeer's energy has been lost due to air resistance during that 100-meter fall? Okay, well, the total energy, sorry, the percent energy is the difference between its total energy and what it has left. I think I said that correctly. I was distracted by somebody running into the room here for a second. So the total potential energy is going to be 45 times 9.8 times 200. That's the total potential energy at the top. What percentage of that has been lost? Well, let's figure out, let me rephrase this. What the percentage of the work, the work done by air resistance is really just going to be that number. It's going to be 16537.5 divided by the total amount of energy, which was 45 times 9.8 times 200. Now I'm on track. Now I caught my groove. So let's just go that. It's 45 times 9.8 times 200. It lost 18.75%. All right. So that's how we would do this one. Jump down to number 7. This is Leonardson Falls. So you can imagine that this water, a bunch of water is falling down from some certain height here. And that height is 125 meters. And it's going to be, it's all potential energy at the top. It's all going to be, it's going to be kinetic energy at the bottom. And it's going to hit maybe some type of a generator, so it's going to spin some wheel. Who cares, really? But so the first thing we got to do is figure out what is the total amount of energy, and then get 65% of that. And then we can figure out the next part. So again, power is equal to work divided by time. So let's figure out the energy, because work is energy. So it starts with all PE, and it gets converted into KE. You're only going to be able to keep 68% of that. So if you take 68% of your PE, that's what's going to be left over for the KE. So let's just do it that way. It's going to be the easiest way to do this problem. So what is 68% of your PE? That's going to be 0.68 times. Now we have 1 meter cubed of water is 1,000 kilograms. So we got to be, this is a really sort of a density conversion. I'm going to skip showing every single step. This is basic chemistry, basic conversions. But if you have, I guess I'm not going to skip, as I say, I'm going to skip it. Here I go and showing it. If you have that amount of water, and 1 meter cubed is 1,000 kilograms, that's how you would do the conversion. It would be 2.5 times 10 to the 4th times 1,000, and then the meters cubed would cancel. So multiplying by 1,000 is really going to up this to 10 to the 7th, right? Because 1,000 is 10 to the 3rd, and then the way you multiply those exponents is to add them. So this 2.5 times 10 to the 7th is the total mass of the water that you have. The G is 9.8 and the H is 125. So let's just quickly crank this one out. And we get a total of 2.0825 times 10 to the 10th joules. Now that's in the order of billions of joules, but that's why we always put generators next to really big waterfalls. And in human history is because waterfalls have been great for generating electrical energy. All right, so what's the power output? Well, this is the energy that we're going to get out of this, and this is this amount of energy we get each minute. So that's 60 seconds, because remember that this time right here is in seconds. So let's just divide this answer by 60, and we are going to get a whole heck of a lot of watts. We're going to get 3.471 times 10 to the 1, 2, 3, 4, 5, 6, 7. Wait, let me double check. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. So it's basically 347 million watts. That's a lot of energy, and that's why we do it this way. So that's how you do this one.